Okay, so in the last tutorial we implemented some rotation control. Sorry, just some rotation. Basically we made a cube that, obeys rigid body dynamics. We simulated its dynamics and then we animated them on a, on a graph, on a 3D graph. This is a very simple thing. We're gonna expand on this tool now and try and implement some rotation control. Originally I planned to do this yesterday, but I had a bunch of issues with some of the signs and yeah, hopefully we can avoid them today. But without further ado, let's get started. So the first thing we need to do when we implement rotation control is we need to define a trajectory, right? We have to define what a desired value is. And so the way we're going to do that is the same way we define, our initial conditions. Our initial conditions we defined as, these Euler angles. We used a converter to convert to quaternions, and that was our initial state vector. We're going to do the exact same thing, but we're going to create a series of what's it called? A series of desired Euler angles, and you'll see why I'm going to why this transpose is going to be necessary. But basically, we're going to do a very simple thing. We're just going to create something that rotates 90 degrees in all three axes, just once. So all of these have to rotate by pi over 2. So I'll just quickly implement that. Pi over 2 and pi over 2. And the way we're going to implement whether or not these values happen, or sorry, when these values happen, is by using a sort of if statement, right? Uh, I'll just do a quick example. So let's say we have a time vector that goes from 0 to, let's say, 3 at this interval. We can see that we have, every value in between, right? And it creates a row vector. Sorry, makes a single row with 31 columns. My apologies. And the way that we can make this into a conditional statement is by simply using, MATLAB's built-in tool. T is greater than, and let's just choose some value 1. And what this will do is this will give us 0 for all the values in which the values in T are not greater than 1, and then a 1 for when they are greater than 1. And you can see that this can be used to create a sort of step function. Obviously, there's a bit of, it's not an ideal step function, and that, between these values there is like a finite time step. But for our purposes, this is more than enough. And when we use a time step of 10 to the negative second, we can more or less pretend that it is in fact a step function. And so all we need to do to implement this is do the dot times, right? So we we're multiplying the whole time vector, or sorry, the whole step function by the rotation. And then to implement it, we just do, let's just say t-span greater than 5, let's say. So the first rotation will happen, so the first step function activates at 5 seconds, the second one activates at 10 seconds, and the third one should activate at 15 seconds, right? Nothing too crazy. And because time span is a single row, we're going to put each column of this as an Euler angle. So this is going to be yaw, pitch, and roll. Whoops. And then we need to transpose that because, our format is the other way around, right? Where we want every row to be a time step. Alternatively, we could just, put a prime here, but I find this to be easier in detecting errors. Once we have that, we just need to convert to quaternions. So QD is just going to be e to q, and we're going to feed it ed, and this will convert everything into a quaternion. The other thing we need is some control gains. So we'll explore more about this later on, but following the paper that we had yesterday, we're gonna scroll down here and we're gonna see that we're gonna be partially recreating the results. They used a PQ gain of 20 and a PW gain of 4, and we'll get into where exactly that's implemented a bit later, but we'll just keep these values stored here for now. Okay, so now that that's done, the next thing we need to do is implement the control into our dynamics. We'll add this in just in a second. So for our dynamics, the main thing that needs to happen, let me just pull up my reference file. I forgot to open it. My apologies. So the dynamics have to change in the fact that we also have to feed it the desired values, right? And we also have to feed it the control gains now. because these are values that, previously in just normal rigid body rotation they don't come into play, but now they do. They come into play for us now. So what does this mean? What this means is that there's going to be some desired quaternion that this dynamics function will try to, go towards, and it will use these control gains to, and some other, whatever the torque generation function is, to do that. So let's just define that right now. So we're going to define our torque as, some quaternion error torque, torque control. And this function is going to take in, like as expected, it's going to take in our current quaternion, Q. It's going to take in our desired quaternion, our omega, and our control gains. And this may seem like I just pulled it out of thin air, but it is from this paper that we are following, in that, forgot to zoom in. For our, dynamics, there was a torque term in here. It's just we didn't account for it. Now we will be accounting for it. And this torque term is precisely equal to the negative of the first gain times our quaternion error, which we'll be defining later, plus the PW gain, the P omega gain times our angular velocities. And this term you just added on to the end of this, right? So we have -1, the cross product of this, plus t. So let's just go in here. So we have -1, the cross product of this thing. At the very end of this, we're just going to do a plus t. Something I know we're going to have problems with is the size of t. So I'll just do display t right now so we can avoid having these errors. And that should be good. All right, so now we have to figure out how to define this function right here. What exactly is this function? Let's do this. So quat etc. So this quat etc function is meant to report out a torque, right? It's meant to get, the output is going to be a torque, and the input for this is, as we've defined before, Q, QD, omega, and K, right? Whoops, I did not mean to do that. Okay, so yeah, feeding it in the Q, QD, omega, and K. Let's go back to our paper and figure out what these values are. So the torque has to figure out what this Q error is. So what is this Q error? This Q error term is defined right here. This Q error is our reference quaternion, which would be our desired, with this Kronecker product of QM star. This star means conjugate. So, let's just implement that. So let me pull up my reference. There we go. So first thing we have is our Q conjugate. So what is our Q conjugate? Well, our Q conjugate is just our Q conjugate is just going to be, how the paper has defined it. Why can I not do this? Okay. In the paper itself, the quaternion conjugate is defined as, we take the first term, the scalar term, keep it as is, and then we just negate the vector. And then we transpose it, which just means, this is a row, this is a single row with 4 columns, we're going to turn into one column with 4 rows. It really doesn't make a difference, but I'll follow the conventions of this paper because the authors definitely know more than I do. Negative Q3 and negative Q4. Okay, so this is our Q conjugate. The next thing we need to do is get our quaternion error. So Q error. And this is just going to be the cross product of our desired quaternions. So it's going to be our PQ. And the first quaternion is going to be QD. And the second one is going to be Q conjugate. Now, something I realized the hard way yesterday, this thing needs to be transposed. Because since we're feeding it, I believe it's because we're feeding it a column vector, this thing is going to turn out to be a column vector as well. We want it to be a row. From here, we just need to calculate our torque, T, and it's going to be equal to negative K1 times our quaternion error, but we're only multiplying the 2 to 4 ones. Let me just pull up the paper again. As you can see, they only multiply the first, second, and third. These are the 3 vector ones, right? The Q0 is our scalar. So times this minus K2 times, and this is just multiplied by our omega vector, right? From the expression we had before. And this should be good. So we've defined our quaternion error torque. Let me go back to our dynamics. Okay, so we have this function defined. We're adding it in. Let's see if there's any more errors that we're going to expect to see here. It all looks good. I forgot to transpose this. Okay, so this looks about right. There might be an error here, but we'll catch it immediately if it does show up. Okay, so we've implemented this, the dynamics into our function. Now we just need to go and change, our simulate function. So before we were only feeding it inertia, now we just need to feed it QD and QK. So first thing we need to do is make sure those values are being inputted. So let's just do this. For our blocks, we also need to feed it QD, and we also need to feed it K now. So inertia, so we have obj.qd equals qd, obj.k equals k, and this should take in both of these values. We also need to define them up here, so we'll just do qd and k, right, because these are now properties. The next thing that we need to do is add them into our dynamics function. So our dynamics function, we just need to do qd and k, but we need to do the appropriate ones. So obj.qd, and we want to feed it the current row with every column. And for the control torques, we just want to feed it obj.k. And I want to say that should be it. Yeah, this looks like it has everything. Oh, whoops, I almost forgot. We need to take our new defining thing here and put this into our parameters here. So I'll just get rid of this, Control V. Yeah, because now we have to account for these two. And everything else is already defined, so let's see how this goes. Rotation, Control, Enter. Okay, it actually defined it. And it is doing what we expect it to do. At 5 seconds it rotated, 10 seconds it rotated, and at 15 seconds it rotated. You may be wondering why that little jitter was there at the beginning. Okay, I think it's just going to run forever. Okay, yeah, the error I had yesterday was one of the signs was wrong, and the way I knew it was wrong is because this thing kept diverging away, right? It kept rotating when it shouldn't have. So the reason why that little jitter happened is because our initial angular velocity wasn't 0, right? It started off with a little bit of velocity when its desired quaternion was supposed to be the origin, which is why it started off moving and then it quickly, the controller quickly brought it back. So now that we've implemented this, the last thing we want to do is implement a way of seeing our data. We're going to call this function cData, and we're going to use this to basically look at our data. This is fairly important in my opinion because, like, our simulation could be running perfectly. It means nothing if we can't analyze it, right, or compare it to other simulations. So we're just going to define. It's going to be a little bit quick, so I'm not going to go too much into the explanations, but we're just going to create a little script that goes through and plots our data. Position, and we're going to make this 100, 100. So the first two are the coordinates from how far away from here it's going to be starting to create it. And then we have the length and the height. So it's going to be made right around here-ish, and it's going to be 900 pixels long and 700 pixels high. Okay, so next thing we're going to do is define t is equal to block dot t whoops is equal to block dot t-span, and then let's just start defining our values. So we're going to have quaternion 1, and we're going to use this as a reference. So we're going to create a subplot, which means there's going to be one big figure, but there's going to be 4 little plots within them, one for each quaternion. It's going to be a 2 by 2, and the very first one is going to be quaternion 1. We're going to be plotting t, and then block dot state s all the rows, first column, and we're going to give it a title of Q1, and we're going to say hold on, and then plot T, and then block dot QD, all the rows, first column. And then we're going to do a hold off. Okay, so if this doesn't make sense, I'll just go through every line one more time. We're creating a subplot. It's going to be a 2 by 2, right? We're going to have 2 plots horizontally and 2 plots vertically, so 4 plots total, 1 for each quaternion. The first plot is going to be quaternion 1. We're going to be plotting 2 lines. First is going to be the simulated value. The second is going to be the desired trajectory. And you'll see that the desired trajectory is going to be a lot more like stiff, and the simulated one's going to be a little bit more of like an actual like response. And so now that we have that, we can just copy paste this thing 4 more times. And let me quickly go back in here and get rid of that display that we had. I think we figured out we had no errors, which is a good thing. So now, yeah, let's just go back in here and go through changing all these things one by one. So now we're going to be simulating, it's going to be quaternion 2. This one's going to be quaternion 3. So that's 3. That's a 3. This is also a 3. This one's going to be quaternion 4. Simulated state 4, quaternion 4, and Q desired 4. Alright, and assuming I didn't make any errors, this should run just as easily. Oops, I didn't mean to do that. You know what, let's just go back in here. Let's just add it down here. And not in rotation control. So we have solution, animation, plus visualization. So what we're going to do is here, it's going to type in C data, and that should execute the C data script. Let's clear CLC and rerun this. So we can see it's already created our block. It's stationary. In 5 seconds it rotates 90 degrees about the first axis. 10 seconds it rotates another 90 degrees about another axis. And the last one rotates another 30 about the last axis. Yaw, pitch, and roll. You can confirm that those were the actual axes. And then it runs a little bit, it runs to 30 just so that we can see if there's any like divergence. And these are the values. Okay, so we can see that, you know, our quaternion desired is, you know, the step functions that we expect it to be. We can see that our desired trajectories are, you know, a little wonky, but they're able to follow along pretty well, right? There's a little bit of overshoot, but we can see that they're, you know, that they are in fact staying at their values, and that there is no like, you know, like wild divergence from them. And yeah, so we can see that we have implemented a rotation control in here. And that should be it for this video. From here, we're gonna go and just, you know, quickly implement it into our, you know, our actual kinetic vehicle. Yeah. All right, that's it for this tutorial.